So the way that it the way it works, specifically down a logical path per se, is at first it simulates thousands of different possible future price paths using the risk neutral measure, or the risk neutral pricing measure, which assumes a risk-free rate. And then for each path, it's going to compute an option payoff at that maturity time. So at the time of maturity, or the ending day, at the time of expiration for the strike price, and it'll compute that option payoff and then average all the payoffs out together from all the different paths. After it averages out, it'll discount the average back to today's using the risk-free rate that we ignored during the risk-free or the risk-neutral pricing. And then that average result after being discounted is what we would say is a theoretical mean for that Monte Carlo simulation. And that should be within a reasonable number of the actual Black-Scholes model pricing of that option. So the payoff functions differ for each market and for each call and put, whereas Asian options will use average prices or barrier options depending on whether levels were hit or not. And the discounted average payoff is usually, like, the factor for that is usually E raised to the negative RT, so R being the risk-free rate and T being the time. And then what'll happen is as the price paths are simulated, there's going to be a term for each rate, or at each step within the formula, that one is going based off, or one term is based off just like almost like an error term that'll kind of be based on the risk-free rate and hold in for any human or just natural error or noise taken into account. And the other term will be based on the random geometric Brownian motion. And this will be repeated off each path and each future price before being added up and averaged out. So one of the biggest things on why the Monte Carlo simulation pricing is so powerful compared to other ways of pricing out options is that it handles other things that other options, exotic options that aren't basically like the American or European or vanilla options per se. And it can also account for multi-asset options like basket or rainbow options, and complex models, and help with complex models involving like stochastic volatility or random jumps that are according to news or not according to natural data. One of the biggest problems with the Monte Carlo simulation is that the computational time that it takes to simulate all these paths and then add them together, average them out, and discount them, it's very slow and very time consuming. Even though it's very accurate, it can be not as helpful as other models. And it's also not ideal, not as effective as other models time-wise, and it's especially less efficient than other partial differential equations like the Black-Scholes or the binomial trinomial tree to find options pricing. But I'd say one of its biggest strengths is the flexibility and the addition to other variables that can be added besides just the stock price, strike price, or the time to maturity, the risk-free rate, and volatility. Other things can be added and other things can be ignored to make it more flexible to how you exactly are trying to use it. And it works for basically any option payoff, whether you execute your option or not, regardless. And like I said before, the complexity and the ability to work with multiple assets makes it probably its strongest strength. Hello, so today I'm going to be talking about the Monte-Carlo simulation and how it's used for option pricing. So the Monte-Carlo simulation, just a little background, is basically simulating large numbers of trials through a distribution, per se, a normal distribution, or for, in our case, a geometric Brownian motion distribution. So, for example, if you were to roll a dice however many times, you would have an average price or an average number that would come out from that dice. So you're able to solve this theoretical mean through different equations leading you to what I have down as 3.5 as the theoretical mean for all the rolls. Now for the Monte-Carlo simulation, what happens is you basically roll that dice, or you have a computer simulate rolling that dice over and over again, thousands or hundreds of thousands of times, or whatever you want it to be, to get what is basically, in theory, that theoretical mean. So what will happen is this diagram. This is a normal distribution for the dice, and what you'll see is we have the theoretical mean on here. But if you were to roll the dice, let's say 1,000 times, you would get a different number each time. If you added up all those numbers and divided by the total numbers that you simulated, you would get the actual mean of that simulation. And Monte Carlo, the way it works is by the law of large numbers. You can actually it'll bounce around this number, but in theory, after a certain number of simulations bottom out at that 3.5 number. So the way this is used for option pricing is more based on there is no theoretical mean per se that you're trying to get to. I mean, if you take the Black-Scholes method per se, assuming the geometric Brownian motion, it's very hard to solve that equation. So what the Monte Carlo simulation does is allows you to take a certain number of simulations, picking out or leading you down a path to a certain options price, and like hundreds of thousands of prices will lead you to one, basically. But see, the thing is with the Monte Carlo simulation is you take on a lot of different variables when you're doing this. You take on things like the stock price, strike price, time to maturity, the risk-free rate, and the volatility.